Welcome to CSC 201, Lesson 4.7, Indirect Argument, Contradiction and Contraposition. A proof by contradiction supposes that the desired conclusion is false. Why? If we suppose that the desired conclusion is false, argue with perfect logic based on that supposition, and reach an impossible conclusion, then it must be that our supposition was incorrect. For example, if we want to prove that Sally paid the parking ticket she received 3 months ago, we would say, suppose that Sally did not pay her parking ticket. What would that mean? We'll play it out. In Sally's town, tickets that remain unpaid for 30 days trigger an automatic collection letter. Since Sally received the ticket more than 30 days ago, she must certainly have received a collection letter. Since she has not received a collection letter, we have reached a contradiction. It must be the case that Sally did pay her parking ticket. So the steps in proof by contradiction are: suppose that the statement to be proved is false. That is, suppose the negation of the statement is true. Show that this supposition leads logically to a contradiction, and then conclude that the statement to be proved must have been true. Okay, our first example of a proof by contradiction. We want to prove that there is no integer that is both even and odd. So the first step of a proof by contradiction is suppose that this is not true. Suppose the opposite. Okay, suppose not. Suppose the negation. So the negation of this statement is that there is. Suppose there exists an integer that is both even and odd. So if we're trying to prove that there is none, we just have to suppose that there is one. That is the negation. So suppose that there is an integer that is both even and odd. Okay. Then, if x is even, that means it can be written as 2k. And if it is odd, that means it can be written as 2j plus 1 for some k and j integers. Okay, so x is both even, it can be written as 2k, and odd, it can be written as 2j plus 1. Thus, 2k has to equal 2j plus 1. They're both the same number. They're both x. And that implies that 2k minus 2j equals 1, just subtracting 2j from both sides there, which implies that if we factor out a 2 from the left, we get 2 times k minus j equals 1, which, if I divide both sides by 2, tells me that k minus j equals 1/2. Okay. We've reached a contradiction because k minus j is an integer. The sum, difference, and products of integers is always an integer, and 1/2 is not an integer. So since k minus j is an integer, and 1/2 is not in the integers, it can't be that k minus j equals 1/2. We have a contradiction. And the symbol for we've reached a contradiction is two opposing arrows facing each other. I don't think your textbook uses this, but I find it satisfying to write that symbol down when I see the contradiction in my proof. Okay, so we've reached a contradiction, which means that we started with an assumption or a supposition, we argued with perfect logic, and we reached something that's impossible to be true. So the only The only reason that we would reach an impossible conclusion is if our supposition was false. So it must be that there are no integers that are both even and odd. Thus, no integer is even and odd. Okay, another example of a proof by contradiction. We want to prove that the sum of a rational number and an irrational number is irrational. So we're going to suppose not, right? Suppose this is not true. That is, suppose the sum of a rational and an irrational is rational. Okay, so now that we have that supposition, we're assuming that whole thing is true. So we're going to let A be, let's call it R. Let R be a rational number. And let S be irrational. Okay, then R plus S can be rewritten as A over B plus S as long as A and B are integers and B is not 0, because R is rational. So we can write it as A over B. We're also supposing that this sum is rational, right? That was part of our supposition, that the sum of a rational and an irrational is rational. So I'm going to say that A over B plus S also equals a rational number C over D, for C and D in the integers and D non-zero. Solving for S yields S equals C over D minus A over B, which we can just get a common denominator and add these things together, and we get we get CB minus AD over BD. And then since CB minus AD is an integer and BD is an integer and BD can't be 0 by the zero product property because neither B nor D are 0. We assumed that earlier in the proof. S is rational. Okay, we've reached a contradiction because we supposed at the very beginning that we were adding a rational and an irrational, right? So we let S be an irrational number. Let S be irrational. Okay, so we've reached a contradiction. Thus, the opposite of our supposition must be true. The opposite of our supposition was the original statement to be proved. Thus, the sum of a rational and irrational number must be irrational. Our next method of indirect proof is proof by contraposition. Contraposition, the root word of that is contrapositive. So argument by contraposition is based on the logical equivalence of a statement and its contrapositive. That is, since a statement and its contrapositive always have the same truth value, if you prove the contrapositive is true, then the original must be true as well. So proof by contraposition steps: express the statement to be proved in if-then form, often done mentally. Rewrite the statement in its contrapositive form, not Q implies not P, and then we proceed with a direct proof of the contrapositive. So suppose not Q, argue, 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 conclude not P, and you've proven not Q implies not P and that P implies Q, because the original is logically equivalent to the contrapositive. Okay, so first example of proof by contraposition. Prove that if the square of an integer is even, then the integer is even. So direct proof would have us assuming or supposing m squared is even, right? And that we would need to show m is even. This gets messy, right? Because m squared being even, that would be 2k for some k and z. And then we need to show m is even, so what do we square root, right? So m is the square root of 2k. How do we, that's hard to manipulate into showing it's even. So the direct proof route is not the way to go here. It's very messy and difficult. Okay, so instead we're going to do by contrapositive. The square of an integer is even, that's my p in the original statement, and the integer itself is even, that's my q. So we're going to suppose not q and argue till we get not p. So we're going to suppose m is not an even integer, and we need to show m squared is not an even integer. So this is not q, and we need to show not p. All right, so not an even, that's an odd, right? So there are only two possibilities, even or odd. So if we're supposing m is not even, then we are supposing m is odd. Okay, so let's go ahead and write the proof. Suppose m is an odd integer. Then m equals 2k plus 1 for some k in the integers. Thus, m squared is 2k plus 1 squared, which is 4k squared plus 4k plus 1, which is 2 times 2k squared plus 2k plus 1. Since 2k squared plus 2k is an integer, m squared is odd, or not even, right? So we have shown that m odd implies m squared is odd, and that is logically equivalent to m squared even implies m even. So let's just write that down. So we showed that m is odd. So the proof is done here. We proved it by contraposition. But m is odd implies m squared is odd, is what we proved, right? And that is logically equivalent to m squared even implies m is even. That's not Q implies not P. Prove using contraposition that for all x and z, so for all integers, if 3 does not divide x squared minus 1, then 3 divides x. So prove using contraposition means I'm going to suppose not Q and prove not P. So let's actually just write down the contrapositive. It says that for all x in z, if not Q, so if 3 does not divide x, then not P would be 3 does divide x squared minus 1. Okay, so that's because this is my Q and this is my P. So not Q implies not P. Now I'm going to prove this statement. I'm going to prove the contrapositive, and then I will have also proven the original statement because a contrapositive and the original statement are logically equivalent. So I'm going to start by supposing the if part of the contrapositive that 3 does not divide x. All right, that means if 3 does not go into x, that means that there's a remainder, right? When you try to divide x by 3, you get a remainder, and the remainders can only be 0 or 1 or 2 when you divide by 3. It's not 0 because that would mean that 3 divides x. So it has to be that x is a multiple of 3 plus 1, or x is a multiple of 3 plus 2. So I have two cases. I have to show that in both cases, 3 divides x squared minus 1, or that x squared minus 1 is a multiple of 3. So let's see, case 1, x equals 3k plus 1. Observe that x squared minus 1 is 3k plus 1 squared minus 1. Just replacing x with 3k plus 1, and that is 9k squared plus 6k plus 1 minus 1, which is 9k squared plus 6k, which is 3 times 3k squared plus 2k. And since 3k squared plus 2k is an integer, 3 divides x squared minus 1. All right, so I proved it for case 1. I showed that 3 does not divide x because it has a remainder of 1. Then 3 does divide x squared minus 1. Now I have to show it for my other case, right? 3k plus 2, remainder of 2. Case 2, x equals 3k plus 2. Observe that x squared minus 1 would be 3k plus 2 squared minus 1, which is 9k squared plus 12k plus 4 minus 1, which is 9k squared plus 12k plus 3, which is 3 times 3k squared plus 4k plus 1. Since 3k squared plus 4k plus 1 is an integer, 3 divides x squared minus 1. So I showed it for the other case as well. So this was an example of both a proof by contrapositive and a proof by cases. Okay, number 10. Prove that for all x and y in z, for all integers x and y, 4 divides x squared minus y squared if and only if x and y are of the same parity. So I actually have two proofs in one here for an if and only if. So if you remember, if and only if, we learned a while back that P if and only if Q means P implies Q and Q implies P. So I actually have to prove two statements here. I have to prove statement 1 is that if x and y have the same parity, then 4 divides x squared minus y squared. That's statement 1 to be proved. And then statement 2 to be proved is the reverse. Q implies P. So that would say that if 4 divides x squared minus y squared, then x and y have the same parity. So I have two statements to prove in order to prove this if and only if. So let's start with statement 1. X and y have the same parity. That means they're both even or they're both odd. So I have two cases, and I'm going to try to prove that 4 divides x squared minus y squared. So this is a good candidate for direct proof, I think. X and y have the same parity is a nice supposition. We have some definitions to work with, and then we can try to show that x squared minus y squared is a multiple of 4. So direct proof for statement 1. Suppose x and y are integers with the same parity. Okay, so case 1, x and y are both even. So that tells me that x is 2k and y is 2j for some k and j in the integers. Thus, x squared minus y squared would be 2k squared minus 4k, blah, 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 blah. X squared is 2k squared, y squared is 2j squared, and that's 4k squared minus 4j squared, which is 4 times k squared minus j squared, which is 4 times an integer. So x squared minus y squared is a multiple of 4. So since k squared minus j squared is an integer, 4 does divide x squared minus y squared. Okay, so direct proof for statement 1. That worked out nicely. Now for statement 2, we wanted to show that if 4 divides x squared minus y squared, then x and y have the same parity. Again, this could get messy, right? So 4 divides x squared minus y squared. That tells you that x squared minus y squared is a multiple of 4. But deducing from here that x and y have the same parity is tricky. Like that's messy. I don't even know, you can't square root both sides. There's nothing I could do to try to show that they have the same parity. So instead of a direct proof, I'm going to do a proof by contrapositive. I'm going to suppose that x and y have opposite parity, right? Not q. And I'm going to show that 4 does not divide x squared minus y squared. So suppose x and y have opposite parity. Need to show that 4 does not divide x squared minus y squared. So supposing x and y have opposite parities, there's two cases. So they could both be even. Sorry, one is even and the other is odd. So case 1 will have x be even and y odd. And then case 2 is we flip it. Y will be even and x will be odd. Then x equals 2k and y equals 2j plus 1 for some k and j in the integers. Thus, x squared minus y squared would be 2k squared minus 2j plus 1 squared, which is 4k squared minus 4j squared plus 4j plus 1, which is 4 times k squared minus j squared minus j minus 1. So we have written x squared minus y squared as 4 times an integer minus 1. So that is not a multiple of 4. So 4 does not divide x squared minus y squared. Okay, so we've proven it for case 1. We supposed that x and y had opposite parities, in particular that x is even and y is odd, and we showed that 4 does not divide x squared minus y squared. We have one more case, so go on to a new page. Our new case is going to be that x is odd and y is even. I just noticed that I forgot to do case 2 of the direct proof for statement 1. We were supposing x and y are integers with the same parity. I did case 1 where they're both even, and then I stopped. I forgot to do case 2. So I'm going to say case 2, left to reader. So I'll let you do case 2 on your own. In the meantime, let's move on to case 2 of the contrapositive proof. Okay, so case 2, x is odd and y is even. Then x equals 2k plus 1 and y equals 2j for some k and j in the integers. Thus, x squared minus y squared equals 2k plus 1 squared minus 2j squared equals 4k squared plus 4k plus 1 minus 4j squared equals 4 times k squared plus k minus j squared plus 1. Since k squared plus k minus j squared is an integer, x squared minus y squared is 4 times an integer plus 1, which means it's not a multiple of 4. So is not a multiple of 4. Alternatively, 4 does not divide x squared minus y squared. And then we have proven it for case 2. We proved the contrapositive for both cases, which proves the original statement.